Please welcome to the stage and prepare yourselves for a high-energy talk, the legendary Viktor Gamov.
Thank you, Bill. Thank you. That means a lot. It comes from people like Bill. So yeah, the question that people always asking, what's the best? Everyone have this like a fear of missing out if you would choose, or like it's called not the fear of missing out. I learned yesterday there's like a fear of better options. It's called like if I choose something, but there are some better options that I'm missing. So it's very similar to fear of missing out. And the truth is, it doesn't matter. By the end of the day, you pick up a tool that will work for your particular use case, help your company to make money or help your business to make money. It doesn't matter. Technology doesn't matter. However, in order to make educated decisions about certain technologies, you need to know and find the ways how to compare. There's only few ways how you can compare certain things. You can pick up the set of features and try to do checkboxes, or you try to implement same use case using different tools and see which one is better. So I actually follow the both approaches in this particular talk. So you will see some of the slides where I will comparing certain things, and after that I will be showing some of the bits of the code as well. My name is Viktor Gamov. Thanks for introduction, Bill. I work as a principal developer advocate at a company called Confluent. How many of you heard about Confluent? Great. So it's a great company founded by original creators of Apache Kafka. And I, as a developer advocate, I really enjoying, oops, give me a second. I'll put this one in frame. I really enjoying doing the conversations with developers, learning from them a lot, and based on those certain conversations, I'm get inspired or creating certain talks or certain pieces of content. And one of the things that I'm doing recently, I'm starting this live stream called Streaming Frontiers. Anyone subscribe to Confluent Developer YouTube channel? So that's the first important thing that you need to do. Just go find Confluent Developer, subscribe, enable notifications, and you will get new videos almost every week where you will learn all things about Kafka, Stream Processing, Flink, and stuff like that. And I'm doing live streams when I'm breaking down certain technologies and I'm kind of like building stuff online. Slides, probably second important slide of this presentation. Slides and video will be available on this channel, on this website. I also put the links to the code, so you don't have to, the typing in links after. There would be a repository of the code. All right, got this? Yeah, you can, at any moment of time, if you feel the urge to tweet about this, my Twitter handle and the Blue Sky handle conveniently placed on every slide for your convenience if you will be tweeting about this. Now, enough of this. What we're going to be talking about today. We're going to be talking, I will be talking, you will be listening, and at the end of the session, you will be able to ask questions. We'll have a conveniently placed microphones. And I will be talking about a thing called stream processing. What is stream processing and how those things are, how you can process those streams. Essentially, stream processing is the set of tools, libraries, frameworks, or what have you, to perform some sort of computation or doing something with events that come in through the streaming source. In general, it doesn't matter of your streaming source, but since current, now inherited Kafka Summit, we're going to be talking mostly about Kafka. In certain cases, in case of Flink, Flink can do not only Kafka. Kafka Streams, in this case, it's in the name, it can do only Kafka. So we're going to be focusing most of the time, not most of the time, we're going to be focusing only on Kafka in this particular talk. Now, two types of stream processing kind of like exist, or two types, or what we like to call, it's a stateless and stateful. And one of the metaphors how I found myself explaining to people is stateless is when every morning you come into your favorite coffee shop place and barista every day, like a tabula rasa, clean slate, doesn't remember you and asking what you want. We don't need to have memories of the past. So the event that you appeared in this coffee shop and barista says, hey, what can I get you? That's the stateless stream processing. We don't need to have any type of state, any type of memory, remember everything what happened within our time frame where we were dealing with this event. Comparing to stateful stream processing, you're showing up to your favorite coffee shop, and barista already knows how many cups of coffee you usually ordered, what's your name, what's your favorite, how many pumps of the sugary syrup you would like to add. And with stateless stream processing, you don't need to have this like a fancy notebook to put the things around. But with stateful, you need to find the places where you will make these notes, right? You will put the information about all these things. So it involves some sort of state. So we're going to be talking about how those two frameworks will be handling state as well. And I think let's jump right in. You will see it's a 2025. There's no presentation without AI-generated cute animals. And this is the attempt to get a squirrel and otter. How you like it? I think it's pretty cool. And no, otter is cute, but a little bit on the kind of like on the fat side. And why is that? Because the logo of the Flink is squirrel, and unofficial logo of Kafka Streams otter. There's still a keep. You can go and vote, so we can have a squirrel as official logo for. The otter of official logo for Kafka Streams. Now we're going to start to setting stage. I'm not going to explain you with the basis of Kafka and how the Kafka send the data. I assume, hopefully, you understand this. Because there would be a lot of assumptions on top of the, since it's already Kafka Summit and /current, you would know at least some basic things. Let's start with Kafka Streams architecture. So Kafka Streams is a library. It's an application library that you put in your application. It's in Java. It used to be, I think it used to be Scala API, but not anymore. Any Scala developers who miss Scala API in Kafka Streams? Okay, that's fine. Okay, you can learn better languages. It's fine. We're not judged, right, about language choices that you choose, but you should find a better language. Now, so let's talk about the application architecture. So it's a library, though this library provides certain interesting things how your application will be interacting with Kafka. So obviously, it's in the name. Kafka Streams rely a lot, or like a lot of architecture decisions rely on architecture of Kafka and how those things communicate with Kafka. Specifically, a lot of scalability aspects of Kafka Streams will rely on a partition count in Kafka topic. Some of the things how it's like even Kafka Streams will rely more on the consumer group architecture. And Kafka Streams is only framework that you get data from Kafka, and the data needs to land in Kafka at the end. And everything starts with Kafka. We have a Kafka topic. The Kafka topic is abstraction that will be materialized in the form of K-stream or key table, which is, if you're a Java developer, will be very much familiar because it has a lot of inspirations with Java collections, Java streams, Java util streams, and how you will structure your program in so-called DSL. I don't like name DSL, to be honest. It's more like the Fluent API rather than DSL. Now we're gonna turn the source topic with source stream, and from this stream we're gonna do around a set of transformation. Inside Kafka Streams application, we have a couple things. A couple of things that will hide some of the low-level things that you would need to implement otherwise yourself. Specifically, how we can deal with operators that require state. So they will manage some local state inside your application, technically outside, because it's going to be instance of RocksDB that's running and storing files outside. We have set of processors. So this Fluent API, this DSL. Yes, we're getting photos. Nice, thank you. Not like this, more like this. so we can have a logo. So in this case, we compile down this Fluent API into the processor API that will be execute each and every operation. Both frameworks, Kafka Streams and Flink, they operate on the concept of data flow or direct acyclic graph, where you have a source, you have a set of operators that you perform sort transformation, and after that you have a sink. In this case, in case of Kafka Streams, as always, will be Kafka topic. One of the things that Kafka Streams also has is ability to see this topology. For example, let me actually show you code before we jump into topology first. So in my Kafka Streams application, Kafka Streams processor, it's the simple click processing functionality. We have a stream of clicks and click of categories of the website, and we'll do some sort of join. And my application topology would look something like this. You don't have to understand this code at the moment because it's just for demonstration of the API and how awesome IntelliJ IDEA draws these fonts on this the high resolution screen. One of the things that starts with this topology, we're reading data from Kafka topic. In this particular case, we're using this class, the stream builder. We're getting stream from the Kafka topic. We need to specify what kind of classes we're going to be using for serialization and deserialization, because we're reading data from Kafka. And as you can see here, my case stream is key value pair. So because Kafka streams rely on the way how messages are organized in Kafka, we have a key and value. So Kafka streams API very much reflects that. So with the this the key and key value pair for stream. Returning to stateful stream processing, the idea is to turn stream into table. Kafka Streams implement this in the form of key table that we can read the data. So we have a stream that comes in form of clicks, and we have some reference data categories of the streams that will store in the topic. So we're going to use this for stream to table join. So we can create this key table. So inside this application, we will be able to look up some certain categories when we need to perform a join between my click stream and my stream of categories. That's kind of like a simple enough. Is it simple enough just to understand the API? And we're going to be operating with the same example when I will be dealing with other framework. And there's whole sorts of things that you can do. You can do grouping, you can do windowing operation. We're going to talk about this as well. And at the end, what we need to do, final operation, we need to send the results back to Kafka. As you can see in this diagram, everything starts in Kafka, everything lands in Kafka. Also, Kafka Streams relies on Kafka not only for data, but also for storing some of the intermediate information. So this K-table state store can be backed by special topic that will contain replication data of this state store. And I will talk about state in a few more slides. Let's take a look on the Flink. Now, Flink on the other side. So Kafka Streams, again, it is a library. It is a JVM-based library. There is implementation that has similar capabilities that comes from Python. But in general, you need to be JVM developer to use Kafka Streams. And there's lots of flexibility you can use with any type of framework, any type of dependency injection. So you will, you do you. On the other side, there's Apache Flink. Apache Flink is a framework, and it's also a computational platform that's able to do any type of stream processing. Kafka is the most popular source and sink for Flink, but it's not necessarily the case. It's a general purpose system. So you don't have to even have Kafka. You don't have to even have a streaming solution. You can just get the data from files in Flink. You do your processing and after that dump back into files. Flink can do that. So there's no like hard dependency of like how it needs to be used with Kafka. And as a result, you can read data from Kafka and send data back to some custom sync, like an iceberg table or something like that. So that's the difference. We have a library. Kafka Streams is a library. And Flink is the framework plus a whole like a computing platform that you need to perform. You, as a developer, you're writing your data stream API, your SQL, or your table API. There's 3 APIs. In Kafka Streams, we have 2 APIs. We have a DSL/Fluent API and the processor API that allows you to perform like a low-level things. In Flink, we have 3 APIs. We have a data stream API, and the news for, where's my Scala people? Flink 2.0 removed Scala API from data stream. It's exciting. That warms my heart every time I say this. They remove Scala APIs in Flink 2.0. We have a SQL and we have the table API. I will show you how those APIs look in a second. You're writing a job, and this job will be packaged in a jar, and it will be submitted to the cluster, to this fella called job manager. It's going to be service that you either run through CLI, or you can iterate over a REST interface, or even through UI. There's a very nice Flink UI where you can submit your jobs. Now, that's the first difference. Have a library, and now this, submitting your job somewhere and executing job somewhere. Once the job will be received, the job manager will be responsible for distributing this job across these task managers where this job will be actually executed. So task manager, can be separate process or like separate machine. So communication between nodes will happen in distributed system fashion. So the things will be moving around the network. Inside the task managers, there's a ways how you can figure how much resources this particular task manager will be able to allocate to run a particular job. So it will be using task slots. And there's important thing is that sometimes people get a little bit confused when they will try to debug some of the errors that happened with their Flink jobs. For example, when they try to figure out why certain jars are absent from when you're executing the job. And these jars, for example, were absent from the task manager, but they thought that if these jars are available in the job manager class path, they're not available in task manager class path. So as a developer, you're responsible for bringing whatever is required for your application, at least for data stream API. For SQL API, you doing something like you creating those nodes and they put these required jars in an instance of the task manager. There was a very great talk from the Robin Moffat for people who try to understand all these cryptic Flink class non-found exceptions. It was also from 2 years ago from Kafka Summit. I recommend you to take a look if you're interested how to configure all this class path stuff. Now. And the task managers will be actually talking to your sources. So your task manager will be talking to your Kafka, will be talking to your connectors, to your sinks and sources, and stuff like that. Now, so that's time for vote. Which would like it better? Do you like the application style? You have your jar deployed in your Java application. Oh, and there's a difference. In Flink, you not necessarily need to use Java. There's a PyFlink that allows you to write jobs using Python. So there's a little bit flexibility. So can we do a round of applause for people who think the Flink has much superior application architecture? Flink? Come on. It's a high energy talk. And let's go Kafka Streams. Okay, we're gonna work on this. It's kind of tight, right? So they're both cool, both nice, and they work great. We'll see. So in this case, Bill will be collecting the one-on-one. So right now it's a tie. So we talk into this one. Oh, I didn't show you Flink. I didn't show you Flink code and how this would look like from the Flink perspective. Now, in the Flink, we're going into data stream processor. So the framework itself allows you to get the data it's a process. Where's my beginning of this application? Also Java application. We start with writing this connection to execution environment. This is where we establish how we're going to be working with the Flink internals. So this execution environment, it's kind of like a sort of dependency injection for Flink when you will be like, I'm running this locally, so right now it will be using local mini cluster. If I will package this job and send this to the cluster, this execution environment will return information about this cluster and how this job would be deployed. The way how it will working with Flink, I need to have a connectors in order to get the data from different sources. So in this particular case, I'm using this Kafka source connector that allows me to connect to Kafka topic. In the concept, in the principle, it looks very similar to what the Kafka Streams does. We also specify how we're going to be reading these messages. So in this particular case, I'm using schema registry, so it will be reading the information from schema registry as well. From what topic, I can set up my consumer group ID, so I can monitor how the consumption is going, and so far and so on. And for the category stream, as you can see here, and there's no keyed information, because Flink doesn't have this notion about what's the keyed stream, what's not keyed stream, but you have ability to tell Flink how to use it. And the reason for that, again, Flink is a general purpose. It doesn't enforce you certain architectural decisions and put them into API. So we still will be able to process Kafka key and values, but you need to do this through changing this API. Same thing we're going to do from Kafka source for reading data from Kafka. And at the other side, I will start at the end. I do have Kafka sync. So in order to send the data back to Kafka, I need to use sync. So in this case, it needs to be extra jars, extra connectors. But again, you have a flexibility to do the stuff. And on top of this, there's a bunch of operations what I can do. We're getting the enriched stream that will include the join between clicks and categories. This is like a join function that I will be processing my joins. Maybe it's like went a little bit overboard with the implementation, but it's like very verbose. There's a lot of things can be done. Or you can use a table API, which is another type of API that you can use inside of Flink. Anyone using this like framework called Jook, J-O-O-Q? Any Java folks? Okay, lady over there. Anyone? No? Seriously. Are you using like Hibernate and stuff in 2025? So the thing about this SQL is actually kind of funny. When I was starting my 20 years ago, my career, I was thinking, I'm not going to learn this SQL thingy. I don't care. I'm a Java developer, right? So I'm going to be, writing my Hibernate code, and my Hibernate code will do the thing. So I don't care about learning SQL. 20 years after, and here we are. We have API that will be interacting with our system. In this case, it's a stream processing system that will use SQL as a DSL to describe the jobs. How crazy is that? So it is what it is, right? So it is that like the existence of SQL inside the Flink doesn't make Flink a database. Hopefully many of you understand. If you don't, on developer.confluent.io or Confluent Developer YouTube channel, David Anderson recorded fantastic video that will explain why Flink is not database. But it's beyond the point of this conversation, but hey, there's a SQL. And the SQL, you can go and create SQL with the old school way, having the string and do concatenation of the string. If you're more advanced, you need to use string builder for this, right? So, but there's even better way. One of the better way is to use table API. So table API, it is very nice. This is more look like a DSL. Also, like a Fluent interface allows you to define the tables inside your in your Java application. There's a table API available for Python, so there's different variety of the things available. Now, Going back to application, so we talk about application architecture, we talk about APIs, we talk about all sorts of interesting stuff. Let's talk about state management, because that's the most important part of the stateful stream processing, right? Whenever you need to do filtering, the mapping, transformation, whatever, it's not difficult. You can do this without stream processing framework. You can do this with the, I don't know, you can use this with Kafka Console Consumer and grep and AWK and some other console tools. It's not hard. But when you need to deal with state, this is where the things will start get interesting. Now, the way how it's done in the Kafka Streams. We're going to start with Kafka Streams, and inside your application, you will have multiple things. We talk about Kafka KStream and key table. Key table can be materialized and stored inside your application instance in the form of kind of the piece of the file. And this state will be stored on your application, and if the application needs to be restarted, this state will be restored. So we're talking about this local state store. Now, in order to survive some of the failures of certain nodes, Kafka Streams has built-in ability to use a replication of this local state store through the changelog topic. What does it mean? So when you're performing some sort of aggregation, you have some Java object that will be collecting this intermediate step. Intermediate data. And this object would be stored locally during the processing. If processing will done, it will dump into file, so you're good. Now, and there will be a process that will pick up these changes in this local state store and send them into changelog topic. So in case of failure of this node and we totally lost these files with the state, when application will restart, it will rehydrate the state from the changelog topic. I think it's brilliant. It's not only putting the concept of turning the streams into table and turning table to streams, kind of like the stream to table duality into play, and it actually uses like all this concept that you were heard from many speakers. In this case, we have a stream that comes from the Kafka topic. We create a table out of the stream, and we also use this table, and we're capturing changes that happens on this local state store, and we will propagate those through the changelog topic. I think it's brilliant. Now, let's talk about how the state management handles in Flink. If you remember application architecture, from the Flink, we do have a task manager that is kind of like a working horse of your Flink cluster. And Flink handles state slightly different because it's a distributed system. You need to think more about how the state will be stored. There's multiple ways how you can plug different state implementations. With Flink 2.0, there's even disaggregated state, meaning that your state can be stored cloud natively in blob storage and S3. And there's two types of things what the Flink can save in terms of state of your application. There is a save points and checkpoints. So, and the difference here is one of these is automatically done. So checkpoints, Flink would be periodically drop the snapshots of your state and the state of your data flow, data stream. And save points, this is something that you can trigger as an operator. Say you need to upgrade your Flink cluster so you can run a save point operation, so Flink will save everything that stores on the nodes, and you will be able to successfully shut down the cluster and do maintenance. And after that, when the click will restart, you can restore the data from the save points. It's also a pretty cool approach. If you are kind of like a distributed systems buff, you probably already know this, but if you want to be a distributed system buff, there's a great algorithm that Flink uses to do distributed checkpointing. As far as I understand, it uses Lamport, a distributed snapshot algorithm. It's also pretty cool. It's kind of like you're trying to create the consistent state of moving thing. And the way how it's done in Flink, it's also pretty brilliantly. I highly recommend you check it out. Now, so we finish with state. The quick reminder, Kafka Streams will use Kafka, it uses combination with a local state store, by default it's a RocksDB, and the changelog topics inside the Kafka. Flink uses checkpoints and save points and you will be able to do pluggable state coordination using like a blob storage or like object storage inside S3. So people, we start with Flink. Who thinks Flink is much more superior in this regard? All right. Who thinks the Kafka Streams is more superior in this case, using the Kafka and stuff? No one. Okay. All right. So Flink winning apparently based on the energy. Okay. So 2-1, 2-1, 2-1. And again, I'm not responsible for. I was just giving you information. I'm giving you things to operate with. Now, scalability. As I mentioned in the very beginning, and you probably already guessed it yourself, Kafka Streams has a Kafka in its name, so it's kind of implies that a lot of things will be related, or the way how Kafka Streams will be handling certain like scalability aspects will somehow be related to the way how we done it in Kafka. So essentially, when we reading data from the Kafka topics, we were using Kafka Consumer, and the Kafka Streams will be using the number of the partition as the number of tasks that will be created inside the application topology. And Kafka Streams is a share nothing architecture. So each individual thread that will be reading individual partitions, they will not, intersect with each other. So you don't need to worry about locking. So some other thread will read the data from another partition. And in fact, the way how it's done in Kafka Streams, we take this topology and this topology instance that we built, from the topic, from the another topic. And let me actually show you this. So there's a brilliant idea in Kafka Streams to have a text description of topology. So in this particular case, that's the representation of my application that you can call Kafka Streams topology.describe. It'll give you text representation. So you can use the tools like a Kafka Stream topology visualizer to see what is going on with your application. So that's my clicks coming, that's my categories coming, that's the state store that will be storing these categories. We're performing a repartitioning, meaning that sometimes we need to have two streams have aligned keys, and sometimes it's not possible because of the data that you're getting. So Kafka Streams makes attempt to repartition and create special topic that will include information that will be aligned between these two topics. So that's why we have a stream between clicks and categories, so they will be aligned, so we'll be able to perform join on this particular topology. And also there's we can have another state store that will be storing some information about unique users, and we're writing this information in the output topic. This topology, this implementation, this direct acyclic graph will be executed inside the special task thread per partition. So each message per partition will be traveled through this topology and will be executed. So you will be, your scalability, the way how you will be able to scale instances of your Kafka Streams application will be pretty much depend on number of partitions of your Kafka topic. Like if you have a situation like you have just one partition in Kafka topic for some reasons, you need to perform some sort of like repartition in order to have a ability to scale the jobs and perform this computation. Each individual thread also manages state for a particular node. So this small database that will be represented state store, or like a state store that created from the key table, or like this one. Each individual thread will have its own instance, and that's why if you will be looking inside the Kafka Streams state application state folder, you'll find multiple files, and each file would be per partition. And let's talk about how the Flink does scalability aspect here. It's a cluster. You have a task managers, and you have a task slot inside the task managers. That's what you do, and you configure for your Flink cluster. You can use either like a manual, manually start and stop the instances, adding task managers to to your cluster. Or you can use the Flink operator and run this in Kubernetes and configure auto scaling, you know, all sorts of things. It's a cluster. It's a computational cluster. So you need to know certain things in order to do that. It gives you more flexibility, how you can assign certain jobs, how they can be executed, and how much resources they can use. Some of the jobs can be more requires like more computation power. Some of the jobs require less computation power, right? So again, Kafka Streams has the scaling on a number of partitions. Here you have a freedom of scaling things. What do you think is better? Like Kafka Streams is better? Or Flink is better? I cannot hear you. Kafka Streams is better? All right. And Flink is better. I think it's a tie. I don't know. Like how tie, right? Okay. 2, 3. Okay. Going next. Now, I have 10 more. Okay, perfect. We're going fantastically. Now, Kafka Streams and Flink can both operate on unbound stream of data. Kafka Streams is designed to be this because this is what we're expecting. Flink actually can operate on bounded stream of data. So Flink's suitable not only for streaming sources, but also for batch sources. But when we're dealing with unbound sources, we really don't really care about like infinity. We really care about the data from certain period of time. So that's why there's different capabilities in both frameworks that allow you to handle this type of situation, handle say like windows. And in Kafka Streams, we have ability to deal with events. We have a different type of windows that we have like a tumbling window, we have a hopping window, we have a session window, different semantics, how the window is moving. But in the reality, kind of like the way how it's implemented, basically you have your state store for a particular operation that you're trying to build a window, and the windowing operation will add another dimension that will represent state that looks over the time. So the way how it's done in Kafka Streams using the window store, and we can perform all sorts of aggregations within the window. If I go to Kafka Stream Processor, do I use any? Let me see if I use. I think I should use some windowing capabilities in my particular case. Yes. So and this is a good example actually. So time window, size of duration, and advanced. So we're going to have a sliding window that will advance like every minute, and the size of 1 hour. Now, the way how a lot of things that happened in the Kafka Streams, it will be very much depend on this kind of like a window semantic, and the way how the late events will be handled is done by defining this like a grace period until what time we should receive messages from the stream, or like consider this message from the stream after this window will be closed. So adding the grace period allows to handle some of the late events. If event arrived outside of the window and outside of grace period, so this event will be discarded. And this is important because the Flink has an absolutely different architecture for handling time and handling the late events and things like that. In the Kafka Streams, it's the windows. It's a bread and butter of stateful stream processing. There's a lot of different semantics. Again, if you go to developer.kafka.io, you can find a bunch of different examples how, say, tumbling window different from hopping window. Now, the way how it's done in Flink, it's done through the concept of the watermarks. And the watermarks would be special type of payload that will be injected into Flink data flow that will be defining or like distinguishing certain like time frames that inside the stream. Again, this would be inserted into into the processing type of topology, but you will not see those in your Kafka, because inside the Flink, there's also a lot of system things that can be inserted into the stream, so the downstream operators will know how to deal with this. So we have this the watermarks that will be generated on the certain mechanism, and they can define how so the system would know where certain messages will land. And then a lot of things will depend on event time, with the processing time, and the way how this time information would be extracted from the individual message, and how this thing will be structured. So there's a whole course inside developer.confluent.io about Flink, and there's a great video that Wade, my colleague, did explain watermarks. So Robin Moffat wrote a brilliant blog post about watermarks. There's like super, he goes like a very deep into going into watermark. But again, it is available in Flink, not available in Kafka Streams, and there's ways how you can handle late event if they will say the watermark can accept. You don't need to define the grace period, so because of the watermarks, and if the late event will arrive within a certain like a time frame that will belong between two watermarks, it will be processed. If not, it will be discarded. Very similar how the Kafka Streams does things. Let me see if I do have an example of this code in my data processor. So we're going to start with, let me go on the very beginning, because it would be much easier to navigate from. I don't see if I use the watermarking generator. I'll take a look after. We have 5 more minutes. Now, exactly once. So exactly once, I don't need to explain you that exactly once, it's the consume, process, produce type of loop that works inside the Kafka, not the produce, store, and consume. Because people coming from the messaging systems, they're thinking this produce, store, consume loop, but we are exactly once implemented in Kafka was implemented. One of the motivations to implement this is to support this in Kafka Streams. And Kafka Streams support this Kafka exactly once, like out of the box. It's just like configuration change, and all things will just start working. Your the processor nodes and the process topology and state stores, they will be kind of like bound, like one message that will go in through all these things will be processed there just once. And it will be handled automatically by producers who can produce in the different topics within one transaction. And we make sure that the state store locally would be consistent with the changelog topic that we sent to the Kafka topic. So it just works out of the box, just a configuration parameter that you need to configure. The way how it's implemented, there's a special type of transaction coordinator that will be making sure that the topics and the consumers, everything would be saved in one transaction. So it is pretty cool. Now, this thing will involve storing data into a state store and sending data over a changelog topic, and also updating the result, like sync topics with that information. Now, with Flink, it provides a framework to support exactly once. There's a framework that allows the developers of connectors to implement and participate into the exactly one processing inside the Flink. There's also involve how internally Flink will handle things, what developers need to be doing in their like connectors in this particular case. As far as I remember, as far as I understand correctly, both source and sync, David can tell me if I'm wrong, but both syncs and source, they support exactly once. Both connectors support exactly once for Kafka. For other connectors, you need to check yourself if they support this. There's the exactly once also covers the way how the data will be stored in the state backend. So again, check documentation if your connector is supporting exactly once. Flink itself has capabilities and tools to support exactly once and have this flow consume, process, and produce flow. I'm gonna skip. Oh, if you want, you can vote about exactly once, which exactly once was implemented better. Flink. Like in this case, okay, implementation for exactly once will be delegated to developers that develop your connector. For Kafka, we have exactly once in Flink and in Kafka Streams. In Kafka Streams, it works out of the box. Who thinks that Flink is better? Like a pluggable architecture, implementing your own kind of the participation in this distributed transaction versus kind of out of the box, batteries included. I'm not trying to influence your decision in any point, not trying to manipulate the decision. Which one's better? Like Kafka Streams or Flink? Let's start Kafka Streams. Okay. And Flink? Okay, maybe it's on me because I didn't go very deep on this explanation, but in this case we have again tie, 3-3, right? So we have one last thing. And one last slide that I want to talk about is yeah, but you know, whatever, like it's a cool story, what we should use. And the answer is always, it really depends on what you're trying to do. For a very long time, I was very comfortable doing Kafka Streams applications, and I'm still comfortable with doing Kafka Streams applications because I'm a Java guy. I like to write my topologies. Speaking, I didn't talk about this, but I should. The testing capabilities, Kafka Streams has this fantastic, fantastic framework, topology test driver, that allows you to run your topology and test your topology without even having Kafka. That's even great. Everything can be implemented as a part of unit test. Let's see if it's, you know, if it runs, meaning that it works, right? So if test passes, ship it. Yeah. Yes or no? Someone should say, what about integration test, Viktor? Yes, and you can do integration tests with both, with the Kafka Streams and the combination with Kafka Streams and test containers. And in this case, you can do integration tests. Before this test, we need to have certain containers. In my particular case, I'm using the schema registry and the CPU Kafka containers before start. When I run this, should run. Should not fail. For Flink, you can do very similar things. So Flink includes this mini local cluster class that allows you to run your topology inside your JVM, so you can perform your tests and stuff like that. Yeah, integration test went successfully. So integration test integrates with containers. Now, Flink data stream integration test. Same thing here. I'm using my containers by using my the test containers that runs Kafka and Flink, and I would just populate information from this Bootstrap server and schema URL into my sink and my source connectors inside in my Flink topology, and after that I run the same method to produce. So in Flink, you already kind of like in the detached mode, and you already much easier can write your integration tests with this type of approach. Now, let me finish this quickly. Kafka Streams, great for microservices. Deployment model is fantastic. You can deploy this as part of the jar. You can deploy this as part of the war, the Docker container, whatever. Topology test driver, easy testing, no need to infrastructure. It's just great, and it just works. Built-in support for exactly one semantics within Kafka. We're talking about Kafka. And very much Kafka-centric. So think about this as a pro or cons. Sometimes you want to do something else. You will be limited only to Kafka. With Flink, you can Google different the testimonials about how massive different organizations might have state. Netflix has some crazy numbers about how much state they store and how much data they process through the Flink. It is computation cluster. It's massive. You have an ability to plug different data sources through the sources and sinks, different components available. There is a unified API if you're dealing with the batching data or you're doing it with streaming data. And you have ability to perform the watermarks. With the watermarks, you can perform different, very complex the time-based semantics in your stream processing operation. Not only Java. You will be able to do SQL. You will be able to do PyFlink. You will be able to do table API for Java. You can do table API from Python. There's lots of things, a lot of cool things that you can do to author your jobs. With this, as always, my name is Viktor Gamov, and I wish you have a great day. We have a tie, right? We have a 3-3, so we don't have a clear winner, because winner is you, because you attended this session, you got some knowledge. So I'm accepting the questions in writing. All the questions must submit in writing. It's from Willy Wonka. Okay, tough crowd. I'm available for enhanced interrogation.